Witness the power of infinite series. A series is the sum of a sequence, and a sequence is an ordered list of numbers. The notation that we use for a sequence is typically a sub n is equal to, and then we list the ordered elements, a0, a1, a2, etc. A series, which uses sigma notation, would be a compact way of saying that we're adding up the terms of the sequence, and some sequences and series are infinite. In a very common example, 1/3 as a decimal is 0.3 repeating, and if we expand that out, it becomes what is called a geometric series. A geometric series has a common ratio and increases by multiplying by a number each time. The simplest example of a geometric series is the series 1 plus x squared plus x cubed, and so on. And if the absolute value of x is less than 1, this series converges to a number given by a function. That function would be 1 over 1 minus x. This function is known as a generating function. It will give the sum for certain x values, but it is also very useful for sequences. Given a sequence, a generating function is given by f of x is equal to an infinite series where the coefficients of that series, which is known as a power series, are the terms of the sequence. And through this infinite polynomial, we can deduce many things about the sequence itself. Generating functions are a great tool in finding an explicit or closed formula for a sequence. So now, given that the general geometric series is given by 1 plus x squared plus x cubed, and so on, and that equals 1 over 1 minus x, if we do a little substitution here, we can find some other series that are interesting, like the series for 1 over 1 minus x squared being 1 plus x squared plus x to the fourth, and so on. And if we let x be negative x, then we get this alternating geometric series given by the function 1 over 1 plus x. Investigating the coefficients of each of these expanded series, we can find the sequence that goes along with each of these series. Here are some other examples of some famous power series. First is e to the x. That function e to the x is given by an infinite power series whose coefficients are of the form 1 over n factorial. Factorial being, let's say, 5 factorial is 5 times 4 times 3 times 2 times 1. By plugging in 1 in for x in this series, we get Euler's number, or just e. Another example of a power series that works in calculus is something called a Taylor series. When we want to approximate a function around a certain x value, we can do so using a series of derivatives as part of the sequence in the infinite series. Therefore, f of x is approximated around a certain point. And if x is equal to 0, we call this a Maclaurin series. Taylor series in calculus are used to approximate many functions, and is one of the ways that you can show that e to the x is the infinite series we saw before. Perhaps a famous problem which was solved by Leonhard Euler using power series was something called a Basel problem, or Basel problem, depending on how you pronounce it. And it's the series of 1 over n squared, or the reciprocals of all the natural numbers squared added together. At the time, it was known that the reciprocals of just the natural numbers 1 over n as an infinite series diverges. That is, it doesn't approach any particular value. But Euler showed that the reciprocal of all the squares summed up to pi squared over 6, a miraculous calculation he did using his power series expansion for e to the ix, employing complex numbers in his infinite series. Something called the Riemann hypothesis is also based on sums such as these. So the Riemann zeta function, defined for a complex number z, is given as 1 over the reciprocal of the natural numbers raised to the complex number z power. And Riemann found there's a connection, Riemann wasn't the only one, that there's a connection between this function and the placement of prime numbers. In fact, this is such a deep problem that the Clay Institute of Mathematics offers a $1 million prize to show that all the non-trivial zeros of this zeta function lie on a line whose real value is a value of 1/2. $1 million prize. Alright, let's take a look at some examples. We're going to find a generating function for a given sequence. And the sequence will be the sequence 1, 2, 3, 4, 5, etc., the natural numbers. So we begin by creating an infinite series whose coefficients are the terms of the sequence. So 1 plus 2 to the x, times 2 times x, plus 3x squared, plus 4x cubed, plus 5x to the fourth, etc. Now, a clever trick also used by Euler was to multiply this series all by x. And what that does is bump up all the powers in the series by 1. Next is to take these two series and subtract them from each other, lining them up by common terms, powers that are equal. And when you line them up and subtract them in an infinite way, we wind up getting a familiar series. The geometric sequence, the geometric series, which we know has a formula which adds up to 1 over 1 minus x. And doing a little bit of factoring here, we can solve for f of x, our generating function, as 1 over 1 minus x quantity squared. That is the generating function for the sequence 1, 2, 3, 4, 5, etc. The Fibonacci sequence, one of the most famous sequences out there, is usually known in its recursive form, but the numbers in the sequence are 0, 1, 1, 2, 3, 5, 8, 13, etc. And looking for a pattern in this sequence, we find that any number in this sequence is always going to be a sum of the previous two numbers that came before it, and so we write that in a recursive formula like this. So where does this thing come from, this idea? Well, first let's explore a different idea in geometry. If I take a segment of length 1 and extend it by a length x, and then consider the ratio of the whole segment to the parts, we get a quadratic equation whose roots are something called the golden ratio, 1 plus radical 5 over 2. It's an irrational number. And there are two of them, plus and minus radical 5. So now, the Fibonacci sequence has a connection to this golden ratio. So if we take the Fibonacci sequence as the numbers 0, 1, 1, 2, 3, etc., and we use the recursive formula, we first have to have two numbers to start with, which are often called the seeds of a recursive formula. Every other number then will be built by adding the previous two numbers in the sequence. So the third number is adding 1 plus 1 to get 2. The fourth term is found by doing 2 plus 1 and getting 3. And so on. 5 is the sum of 3 plus 2. Question is, what is the 10th term of the Fibonacci sequence? Now with a recursive formula and the 10th term not being that much further down the sequence here, we can just build it term by term and it's not a problem. So we can find that the 9th term will be 34, and the 10th term works out to be 55. Okay, so easy enough to find that the 10th term of the Fibonacci sequence is 55. So then, here's a question for you. What is the value of the 100th Fibonacci number in the sequence? Well, we wouldn't want to do that term by term. That would take a long time and be inefficient. So we need an explicit closed form formula for the Fibonacci sequence, one that tells us exactly what the number is by plugging in n equals 100. So what we're going to do is we're going to begin by constructing a generating function for the Fibonacci sequence. That is, we're going to use the Fibonacci sequence as coefficients in an infinite polynomial. The sigma notation is just a shorthand way of saying that we're summing up all of these types of terms, starting with n equals 0 out to infinity. Now, if we multiply this sequence, or this series, by x, we're just going to multiply it through all of the terms in that expanded form and bump up the powers of x by 1. Now, like we did before in a previous example, we're going to try to subtract some sequences or add them together to see a result, but what we're going to also need here is to multiply this sequence with x squared, bumping all the x's up by a power of 2. Now, when we start putting some things together, like adding these two particular sequences together, x of f of x and x squared of f of x, then we have a new sequence pop out, and just adding things term by term, coefficient by coefficient, we begin to see something that is a little bit familiar. This sequence here is the same as adding 1x plus 1x squared if we add x to both sides of this equation. Right, so what I'm doing is we're trying to look at the sequence that has resulted in adding the two series together and then playing around by manipulating both sides of the equation to make one side look like the other. And eventually we get this generating function, x over 1 minus x squared, as the generating function for the Fibonacci sequence. So playing around with infinite series is a really good thing to practice to see how these generating functions work. Now, what we're going to need to do to find an explicit closed form formula for the Fibonacci sequence is, here's our plan of action. There's a couple of steps. So step 1 is going to be to decompose this rational expression, this function, into partial fractions. Then we're going to try to rewrite those partial fractions in a way that we can relate them to the geometric series of the general form 1 plus x squared, etc., which is equal to 1 over 1 minus x. So our partial fractions will look something like the right-hand side of that equation. And then we'll extract the explicit form from it. Partial fraction decomposition begins by factoring the denominator and finding the, if you can, linear factors here. So the denominator here is a quadratic, so we're going to find two linear factors by first finding its roots. And with a little bit of manipulation and the quadratic formula, we see that notice that the roots here are the negative of the golden ratio. That's pretty neat. So what we're going to do is write out the linear factors for this quadratic as x plus phi1 and x plus phi2. Now, partial fractions begin with the idea that if you have a fraction with a product in the denominator, you can split it up as a sum of two simpler fractions, each with a denominator of one of those factors. So that's what I'm setting up here, and a and b just represent some real constants. Then recombining those two fractions as we would like with common denominators, we get an expression which we set equal to the original function on the left, and then we can compare their two numerators as being equal since their denominators are equal. That gives us something called a primary equation, where a and b can be solved for by selectively choosing careful values of x. And here I'm going to be choosing the roots that we had. First one is going to be x equals negative phi1, and by plugging that in, we get some things to cancel, and we can solve for the constant b. And all I'm doing right now is manipulating the values of phi1 and phi2 in this to get the simplest form before I actually evaluate them. To get a, we're going to let x equal negative phi2, and that gets b to drop out, and then we can solve for a. a little cleaning up of the a and b values now by looking at what their denominators are as numerical values. We find that the b has a numerical denominator of negative radical 5, and a has a numerical denominator of positive radical 5. So writing this in a more simplistic way, we get the values for a and b. Next, we can now substitute those in as the partial fraction decomposition of that rational expression that we had for f of x. The next part of our plan of action is to look at those fractions and think about them in the form of a geometric series. So we would really like the bottom to read something like 1 minus x, but for each of those factors we have like x plus phi2 and x plus phi1. So with a little algebraic manipulation and multiplying the top and bottom of those fractions by some cleverly chose constants, we can get the denominator of that fraction to look more like 1 over 1 minus x, like we remind ourselves a geometric series looks like. So now, filtering out some of those constants, we get some things to nicely simplify in our equations. And what we find here is that we get 1 over the square root of 5, inside the parentheses 1 over 1 plus x over phi 2 minus 1 over 1 plus x. That should be, yes, so 1 plus x over phi 1. And extracting out some negatives because we really want it to be 1 minus that, we start putting them into signal notation and collecting the terms here. So you may want to pause the video after this is done just to carefully look and see the sequence of steps out here. But now that I can recombine them into one compact sigma notation by relating them to have the same powers of x and simplifying some of the expressions using conjugacy, we get f of x to be equal to 1 over radical 5 times the infinite sum of phi 1 to the nth minus phi 2 to the nth times x to the nth power. So looking at the coefficients of our generating function, we get f of n is equal to phi 1 to the nth minus phi 2 to the nth all over radical 5, a closed form for the Fibonacci sequence, albeit a rather complicated looking formula known as Benet's formula. This is now going to help us calculate the 100th term in the Fibonacci sequence directly or explicitly. So what is the 100th Fibonacci number? It must be some big number. And using our formula by letting n equal 100 and perhaps a supercomputer to help us get all the digits, we arrive at the number 354 quintillion, 224 quadrillion, 848 trillion, 179 billion, 261,915,075. I wonder if a plant exists with this many number of petals, as the Fibonacci numbers tend to be the number of petals on many or most plants. Bet you didn't know that. Anyway, I hope you enjoyed the video. Please like, subscribe, and hit that notification bell for more videos, and stay tuned.